All right, so we had loads of fun with tension. Now let's look at the normal force. The normal force is a force that's due to any surface. And so if I have an object sitting here on a table, if I were to make the free body diagram for it, I have Fg always acting downwards, and another force must be acting upwards to keep this block in one place and it's not accelerating, and that is the normal force. And so the normal force for an object at rest will be equal to the gravity force that is pulling it downwards when it's on a flat horizontal plane like this. And so again, I could say that Fn minus Fg equals 0, or Fn equals Fg, which is mg, which would be again the mass of this object times g. And so that is a normal force that is holding it in place. Really simple to figure this out. Again, if this block was, say, 5 kg, or let's make it, 5 kg, and this was the same case, then Fg would be 5 times 9.8, or 49 newtons. So that is also going to be the same as my Fn. So my normal force can be easily calculated by simply using this simple formula. Now, what if this thing was actually an elevator and I have a mass sitting up here? Now this elevator, this whole thing was part of an elevator, and it was moving upwards, let's say at 2 meters per second, just like we did in the case of the tension. Again, since there's no acceleration, Fg, which is acting in the bottom direction, plus Fn would equal to 0. Again, Fn equals Fg, and so that would still be 49 newtons. So the normal force experienced by this block would simply be 49 newtons. Same thing would be happening if this elevator was moving down, let's say at 2 meters per second. Again, I would have Fn minus Fg equals 0, Fn equals Fg, which is again going to be m times g, or 49 newtons. So we see in the case of the normal force, it's the same if it's again constant, because there's no acceleration. What would have been ma here is 0 because the a is 0. Now, when you ask about your weight, or you feel your weight, you never really feel your weight. You stand on the floor, you're feeling the normal force from the floor acting up on you, and that's what you determine to be your weight. The weight that you feel, or your weight that you feel of yourself, is simply the normal force acting up on you. So if this were an elevator and this was you standing on the elevator, while the elevator is moving up or down at a constant speed, you don't even feel like it's moving. You don't feel any special forces on your floor, on your feet. However, that's not the same when your elevator is increasing or decreasing in speed, which happens when it first starts up, or first starts going down, or first starts going up. You feel either you get a little lighter, or you feel like you got a little heavier, depending on what the elevator was doing. So let's examine that in a little detail. So let's say that this was a mass on an elevator moving upwards, and really you could put a scale out here. So imagine if you're standing on a scale. Let me just redraw this picture. Here's you standing on a weighing scale on an elevator. And now let's make this elevator accelerate upwards at 2 meters per second squared. So now when I make my free body diagram of this person, they have force of gravity acting downwards, but the normal force on their feet is larger because they're accelerating upwards. So then we have Fn minus Fg is equal to some mass times acceleration. And so my normal force then becomes Fg plus Ma, which becomes M times G plus Ma. Recognize the term again, be like M plus G plus A. And so my normal force would end up being 3, or if I'm using 5 kg in this case, so let me put that, use the same numbers. So it'd be 5 times 9.8 plus 2. And so that becomes my new force of gravity, or not my new force of gravity, but my new felt normal force. And you could see that it would be 49 plus 10, or 59 newtons. So while you're accelerating upwards, the normal force is larger than your mass and your weight, and which is why you feel heavier, because remember, your perception of weight is simply the normal force acting on your feet. So again, if you notice that when you are on an elevator and you're at the ground floor and it starts to move upwards, for a moment you feel like you just got a little heavier until the elevator comes to a constant speed. And so that's what's going on here, which is why your normal force, which you would feel at 49 newtons, is now 59 newtons. If you were coming down at 2 meters per second squared, then my free body diagram would look like this, where Fg is larger than Fn. And so I would write that as Fn minus Fg equals minus Ma. Again, the negative sign is because we are accelerating downwards. And so that tells me that Fn would be Fg minus Ma, or M times G minus A. And so that gives me my normal force as being 49 minus 10, or 39 newtons. So that is the force I feel when the elevator is accelerating downwards. And again, so if you were at the 10th floor and you push the button to go down, the moment it starts to move downwards, you feel like you just got a little lighter. Usually gives you a little butterfly feeling in your stomach. And that is what is going on here. So you feel lighter for that period of time while the elevator is moving downward. So here, that solves your mystery on why do I feel heavier or lighter as I ride the elevator at different points. Again, notice that when you are moving at constant speed, you feel the same force, and you're not feeling any heavier or lighter during those points. I like to call this elevator physics, and so I hope this makes sense on how to go ahead and solve problems like these. And so that'll end this little lecture on elevator physics.